Let's now talk about mechanical definitions. There are many definitions, but I decided, for the sake of clarity, to keep only the most important definitions. The most important is the failing load. The mechanical failing load is the maximum load an insulator can take before it breaks. So when you test an insulator, you pull on it with the pull testing machines. The value at which it breaks is what is being called the mechanical failing load. This value is higher than the second definition, which is the specified mechanical failing load. The specified mechanical failing load is the maximum load that the manufacturer will guarantee to a customer. As an example, if you have an insulator which is rated with a specified mechanical failing load at 120 kilonewton, you will not be allowed to have a failure below. And usually the mechanical failing load is above. When we design insulators, of course, we make sure that the mechanical failing load is above the specified mechanical load. But you have probably seen some testing, but when you test 20 insulators, they're not all 20 going to fail at the same value. They are slightly scattered around an average value. And you need to be absolutely sure that when you calculate a standard deviation, that the average failing load minus 3 or 4 standard deviation stays above the specified failing load. So contractually, when we sell insulators, we are bound to the specified mechanical failing load. This is the one you have to verify with the customer to make sure your insulator is what you promise. There is another load called routine test load. Every insulator, I really mean it, every insulator, 100% of everything that is produced goes through a routine test load. This is a mechanical load that is applied on every insulator at the end of manufacturing to be sure that manufacturing is okay. Now, you can tell me, okay, so we know that the routine test load verifies that the insulator is safe, but if we pull it, don't we create some damage to the insulator? Well, the routine test load corresponds to 50% of the rating, half. Why half? Simply because in service, an insulator is typically subjected to 30% of the rating. In some exceptional cases, it can go to 50, short-term extraordinary loads 60, 65, or 80 for a few minutes per year. But you do not, in normal life, exceed 50% of the rating. And these are safety factors which are integrated in the design of a power line. So when you test in your factory every insulator with the routine test load at 50% of the rating, you know that your insulator is going to be good for service conditions, and you would not expect anything else to happen. There is another definition which is existing mostly for porcelain insulators. It's what we call the M&E, which is described in American standards. The M&E is a rating which combines an electric stress and a mechanical stress. When you pull on an insulator, on a porcelain insulator, you could degrade the structure of the porcelain body, so that when you do an M&E test, that you do not damage the structure of the material under the specified value, with consequences which are not necessarily mechanical, but because your insulator might not separate or break in pieces, but you could have a small crack which can be an electrical problem, which is what we call a puncture. We will see that also later on in a few minutes. So for porcelain, you have an M&E test, which is an electromechanical guarantee, rating, failing load, and you have an electromechanical routine test. Porcelain insulators, when they are manufactured, talking about cap and pin insulators, which are, I would say, the twin brothers of glass cap and pin insulators, are tested in routine with an electromechanical stress. Okay, so here you see what I said earlier. Service load is around 30%, which is why the routine is around 50. You have two other words which exist when people are talking about performance of insulators and tests in the laboratories. One is what we call a thermomechanical test. This is a test where you combine a mechanical load with variations of temperatures. You see on the graph at the left, the top graph shows you that the insulator is subjected to a mechanical load for 24 hours. Then the load is released. Then it is reapplied for another 24 hours, and so on for 96 hours. So you have mechanical cycles which last 96 hours. Simultaneously, you apply variations of temperature, which will last 96 hours as well. In IC, temperature variations are from plus 40 to minus 30 Celsius, up and down. The Canadian climate being a little bit different from most other climates, the Canadian standard is actually asking that you do this test with a variations of temperatures that goes from minus 50 to plus 50 Celsius. And of course, at the end of the test, you make a mechanical assessment of your insulators with a mechanical test if it's glass insulators, and the M&E electromechanical test if it is porcelain. This test is a test which you don't do every time you produce insulators, but it's what we call a type test, which is a test you do once to demonstrate that the design of your insulator is okay. There is another test which is known in our industry. It is called residual strength test. This is a test where you are going to pull mechanically on your insulator, but only after the insulator is being broken. So you take a hammer and you destroy the skirt. This is a test you do on toughened glass or on porcelain. You destroy the skirt. When the skirt is gone, like you can see as the picture on the right side, you pull mechanically on the insulator. Again, what is expected through this test? What you expect through this test is to show that your insulator, if it is broken, is still capable to hold 65% of the initial rating, the guarantee that the manufacturer gives to the end user. 65%, if you remember what I said earlier, a everyday load on the line is around 30%. So if you can guarantee at least 65%, you know you are good. Sediver gives a guarantee of 80% minimum if the insulator is broken. For many, many years in international standards, Sediver tried to get the 65%, which is in the standard, to 80%. It is very interesting to see that the porcelain manufacturers always refused the 80%, which shows that there is more risk with a porcelain cap and pin insulator to have a separation of a broken insulator at lower loads compared to a toughened glass insulator. The electromechanical test, which I explained earlier, you see here, there is a cross-section of a porcelain insulator which failed in this electromechanical test. And you see there is a black crack, a black line in the head of this insulator, which is what we call a puncture. A puncture is a path across the thickness of the porcelain body, which makes that if you have any arcing activity on the insulator, the arc will actually take place in this crack. And this means that your insulator is no longer capable to do its job. on a string of insulators if you have a porcelain disc that is punctured, and if you have a lightning on the line, the increase of voltage resulting from this lightning can generate an arc inside this crack of the porcelain insulator, and the energy that is accumulated during this lightning will make that your insulator will actually blow up in pieces. Typically, you have the metal cap, cast iron metal cap, that breaks in pieces and you drop the conductor, or you have the pin that is ejected by the energy going through this arc. Which is why for porcelain, as I said earlier, you have a test which is called the M&E test, the electromechanical test, which is a test where you apply simultaneously an electric voltage while you actually increase the mechanical load during this test. The graph you see at the right of this slide shows you M&E test results from all the insulators which have been removed from a line in Canada. It's a very interesting exercise which we did in one of the Sediver laboratories some years ago. It's a 735 kV line that was relatively old, 47 years old, and the utility started to believe that those insulators start to give problems in terms of maintenance. There is some risk. So they took insulators down and we tested them for them in our lab. You see the red line on the graph is the mechanical rating. And you see that there are plenty of dots above and below this line. And the blue dots are actually points of the tests where you actually break mechanically the insulator. The orange dots are failures of some samples because of electrical puncture during the application of the mechanical load. And you see that, and this is typical of old porcelain, you see that from a mechanical point of view, they are typically still capable to hold a relatively good mechanical stress, but you have electrical risks because the porcelain body itself has aged and you have small cracks which under the M&E test just break. So when you calculate, if you remember, I said you calculate standard deviation. If you look at 2 or 3 standard deviation, you see that these insulators, if you take the M&E global average value with the standard deviation, is very low. It is the orange line that is with 3 sigma, which means that you are almost at the everyday load. So you have a risk at any point in time to have a line drop during the life of this line with those insulators. And as a conclusion, this customer has decided urgently to replace all the insulators. This is something that does not exist with glass because toughened glass cannot be punctured. So you don't have any aging from toughened glass because unlike porcelain where you have a crystallographic structure in the material, toughened glass, there is no structure. It's a frozen liquid. So the beauty of toughened glass insulators is that the market and the standards have recognized that there is no value to do an electromechanical test with toughened glass. Therefore, with glass, we only have mechanical testing. There is no electromechanical test required.